speaker is a world-renowned expert in the fate and transport of legacy and emerging chemicals and leads the development of non-thermoplasma technology to destroy PFAS in water. He is a board certified environmental engineer, chief technology officer of DMAX Plasma, and a key investigator on several Department of Defense projects regarding contaminant removal. So he knows a few things. Please welcome Dr. Thomas Holsen.
Thank the organizers for inviting me to come talk about a topic that has occupied my professional life for about 15 years. I'm sure you've all heard something about PFAS. It's a big, broad topic, so I'm going to cover some of the key things about its chemistry, how it came about. Talk a bit about treatment challenges and some take-home messages. So I don't want to get too much into the chemistry, but it's an important part of the story. So PFAS, per and polyfluoroalkyl substances. A lot to unpack there. Just a few things. Per just means all, so these intersections are carbons not labeled here. All the carbons have fluorine on them. There's two big classes, the carboxylates and the sulfonates. So the difference is this head group, and I'll talk about a little bit about why that's important. This backbone, this carbon-fluorine tail, can have different lengths. It can be quite long. If they're very long, they're very hydrophobic. They like to get onto bubbles. They interact with biological membranes. Then the polyfluoral just means that some of these fluorines are substituted with carbons. And these compounds are well known. We know what they are. They're easy to measure. These are, many of these are unknown. We don't know what they are. We don't know how to measure them. I'll talk a little bit about why that's important as I go on. So there's classes we know a lot about, PFOA, PFOS, the most well-known compounds, a whole bunch of things we've been discovering, and there's thousands and thousands of other compounds. I'll talk about where these come from. When these were made, they weren't made directly, they were made indirectly. So there are many, many compounds that we don't understand, we don't know how to measure them. And I'll talk about why that's important as we go along. So let me just talk about PFOA. This is the most well-known PFAS compound. It has 8 carbon molecules surrounded by fluorine. So it's very soap-like. You can easily get it on bubbles. Interacts with membranes. This carbon-fluorine bond is the most stable bond in chemistry. That's why these things are very hard to remove. They're very firmly stable. So pKa, not so important what it is. All it means is when the pH is above 2.8, this hydrogen comes off. So this becomes an anion. I'm an environmental engineer, worked my whole career trying to remove these from water. And organic anions, unknown. We don't know what to do with these compounds. They're very water soluble because this hydrogen comes off. So I'm not sure, let me back up just a second. So the pH is above this number when they're anions. So environmental pH is around 7. This hydrogen comes off, and this is an anion. That means it's extremely soluble. You can dissolve lots and lots of PFAS in water. When we remove things in water, they're typically low solubility, we know how to deal with them. High solubility compounds, very difficult to separate from water. So I don't want to talk too much about the history, but I'll go very quickly through this. So 1951, DuPont started making Teflon. We're all very familiar with Teflon. To make Teflon smooth on surfaces, you have to add PFOA. So when I was a kid, you could see advertising PFOA and pans. You don't see this anymore. So DuPont started looking at these compounds, and you can go through this history. I encourage you, if you're interested, watch this movie, Dark Waters by Mark Ruffalo. talks a lot about the early history of PFAS and how it was determined that it was causing environmental impacts. So just quickly scroll through these. These are studies, 3M and others, that were sponsored by DuPont, finding that there were environmental impacts. None of this was disclosed to the general public or EPA. They started removing employees from factories when there were impacts. Didn't let women work in these factories who were making PFAS anymore. Again, none of this disclosed to the EPA. Heightened cancer rates in their workers. The story goes on. EPA started getting involved in the early 90s, into the 2000s. Lots of money's been spent. Importantly, in this room, everyone must have measurable amounts of PFAS in our blood. So there's lots of regulations going back and forth. These are the 2002 ones before the current administration. These have been going up and down. It's not so important what the absolute number is. There's a few things I want to point out. So health advisory levels. So these are levels that they think has to be lower than this number in water to have no effect. 0.004 parts per trillion. These are levels we can't even measure in our laboratory. We have a state-of-the-art PFAS laboratory. Too low for us to differentiate between a clean water and water that has this levels in it. Minimum reporting levels, these levels we can measure pretty easily. Just to give you some context, so 4 parts per trillion. So what does that mean? That's nanograms per liter. It's hard to know what that means. But let's compare it to a chemical that we know is toxic, benzene. Right, everyone think benzene, oh yeah, that's a toxic chemical. Maximum contaminant level for benzene, 5,000 nanograms per liter. These levels that we're worried about, 3 orders of magnitude lower in water. So a big problem. So where are PFAS found? There's a great website, Northeastern University, to search PFAS. They have compiled and continue to compile all the data that's available on PFAS in the environment. So on the left side, right here to see the back, these are known contaminant sites. There's one quite close to where we are right now. That's certainly Fort Drum. Based on GIS and other data, they predict probably all of these places have PFAS contamination in the water. Toxicity concerns. So where did PFAS come from? The main source is AFFF, aqueous film-forming foam. These foams were made to put out fires. If you remember, if you've seen fire trucks spraying foam, that foam is PFAS. They're actually very, very good at putting out fires. So based on the history, DuPont knew these were toxic. Here's someone at the Air Force spraying it on their wives and kids, unknown that it is toxic. Some videos missing, that's all right. So PFAS, every military site trained with PFAS in their foams. Right, so every military site has a problem. Airports have a problem. I'll talk more about that as we go. But one note though, so I'm talking about all the problems, but certainly AFFF has saved lives. Right? DOD is spending millions of dollars trying to replace these foams with non-fluorine containing foams, which is necessary. Right? But they're trading off saving lives. If you're in a ship and there's a fire, you want that fire out as quickly as possible, right? So it's a balancing act DOD is going through to try to replace these AFFF compounds. PFAS on our plate, easily measurable in many of the foods we eat, in packaging containers, all that use films that don't store the water. Many of those contain PFAS, no longer. When I was a kid, we used to have Scotch Guard. I don't remember you in the room. Scotch Guard contained PFAS, right? You can't find it anymore. It's actually taken off the shelves. Before, this was a big worry publicly because 3M knew that this was going to be a problem. So back to sites, maps are so important. So where are the big problems? So landfills, where we had in our products would go to landfill, the landfill leachates have lots of PFAS. Lots of work being done on how to remove PFAS from leachates. The main disposal of leachates is into our wastewater treatment plants. So landfills, they have to get rid of the leachate, it goes into our wastewater treatment plants. So that's a big source to the wastewater treatment plants, and I'll talk about that in a minute. Airports, electroplating and metal finishing, they use PFAS to keep the planing baths from getting to the atmosphere, and wastewater treatment plants. Certainly a big source now. The environment-wide wastewater treatment plants. Some of these slides are out of order, sorry about that. Phased out, there's lots of headlines about PFAS, I'm sure you've seen them. School uniforms, one of the new ones. Hemispheric source, again, this out of order slides, I'm sorry about that, but so I've been talking about water. There's also evidence that factories release PFAS through stacks, through high temperature processes, and evidence that it can contaminate downstream locations. So back to wastewater treatment plants. So we've got these PFAS going into a wastewater treatment plant, many of which we know, many of which we don't know what they are. They're in a wastewater treatment plant. Some of them can partition into sludge. Lots of problems in Maine. Sorry, I should back up a second. So the sludge has high nutrients in it. What do wastewater treatment plants do with their sludge? They give it to the farmers to spread on their fields, to grow crops. Well, a usual way to get rid of wastewater treatment plant sludge, make use of it. Unfortunately, it's contaminated in Maine, contaminated a lot of the farms. So they're trying to deal with that problem now, figure out what those farms can still produce safely. So through a wastewater treatment plant, generate some sludge, go to our aeration basin. These unknown PFAS, unfortunately, can be converted to these PFAS that I mentioned in aeration basins. So wastewater treatment plants, and this slide, I'm sure you're not going to be able to see in the back, it's not so important. So these are just categories of PFAS. The first bar is in, the second bar is out. This is all the data that was available when this study was done. And if you just compare pairs of bar charts, you see wastewater treatment plants do a lousy job of removing PFAS. Not surprising, they're very soluble. You can't break the carbon-fluorine bond. They do partition to sludge, so that's one way they can remove them. They also make PFAS in their aeration process. These weren't designed to remove PFAS. Not surprising, they don't remove PFAS. They don't remove many of the common environmental contaminants that we're worried about. Another kind of busy slide, not so important, the details. I just want to point out this gray bar. So this was study done on the effluent coming out of a wastewater treatment plant. These bars, the top bars, the hatched bar, the black bar, these are PFAS we can measure. This gray bar are PFAS we can't measure. Let's say we can't measure what we don't, I should clarify, it means we don't know what they are. There are indirect ways to get at PFAS. You can measure just the fluorine in the water, organic fluorine containing compounds. So these gray ones, maybe half of what's going out of these wastewater treatment plants, we're not tracking, we don't know what they are, we don't know what their environmental problems are. So, I spent a lot of my effort working on treatment options, right? We need treatment options for these compounds. Lots of money being spent, lots of effort being made to improve these processes. So I'll talk about separation processes, so just getting the PFAS out of the water into some other phase. Membrane filtration, foam fractionation, sorption. I'll talk briefly about each of these, and ion exchange. So well-known processes, trying to tailor them to remove PFAS. Again, they're indirect towards moving them to something else, some other phase, getting them out of the water. There's still a waste you got to deal with. The destructive technologies is the area I'm mostly working in. How do we break the carbon-fluorine bonds so that these no longer become a problem? And I'll talk about these: electrochemicals, supercritical water oxidation, halt, non-thermal plasma. So briefly, I'll go through each of these membrane processes. Well-known way to treat water. Basically, you have a membrane with a pore, some known pore size. If that pore is smaller than the molecule you're trying to remove, then it can't get through. So reverse osmosis is how we make drinking water out of seawater. Right? Process works well. It's expensive, but it does remove PFAS from the water. It generates a concentrate. So maybe 90% of the water goes through, 10% remains. You have to do something with this 10% that contains the PFAS. It can be expensive and it's concentrated stream, so that's already talking about. Foam fractionation, this is a big one. People are spending a lot of effort. As I mentioned earlier, most PFAS have this long carbon-fluorine tail. They're very soap-like, so if you bubble gases through water, you can remove them from the water. And there's commercial processes, several companies working hard at this. Works well for landfill leachates and other concentrated streams. Removal is chain length dependent, so the shorter chain compounds, the probably less toxic ones, are not removed as well. Carbon-based sorption, so this is kind of the standby process for environmental engineering to remove contaminants from water. It relies on the compound preferring to be on a carbon surface than in the water. Works very well for low solubility compounds. As I mentioned earlier, these are pretty high solubility, so they don't work very well. And the shorter the chain, the less it dislikes being in water, the quicker it breaks through carbon. And importantly, there's many, I can see this in the back, but there's many other sorbents. Lots of money being spent tailoring sorbents directly for PFAS, and this certainly be a solution going forward. Ion exchange. Anyone have water softener in their house right now, or has in the past? So that's the exact same process. So an ion exchange process, you remove a compound you don't like and replace it with something that's not less toxic. For water softeners, you remove hardness, you're removing calcium, magnesium, and when we're removing them, we're putting sodium into the water. You can do much the same with PFAS. I mentioned they're anionic. So if you get a cationic ion exchange resin, you can sort them to the resin. In this place, you typically would put the chloride back in the water. Then after time, you can regenerate these resins and generate a very high concentration PFAS waste stream. And we're working hard on that. So this slide just compares carbon with ion exchange resin. So this is influence, so effluent, so this red is the carbon. So we're starting to see leakage, the PFAS breaking through the carbon, not breaking through the ion exchange resin at all. So this is being used in industry, one of the go-to processes for PFAS treatment. Some more novel ones now, electrochemical oxidation. This is where if you get a PFAS to a surface, you can break it with electricity. Several commercial processes, we're working on this at Clarkson, Professor Yang. The challenge with this process is you gotta get that large molecule to a surface. That can be slow and difficult, so removal can take a long time and can be expensive. Supercritical water oxidation, there are 3 commercial companies doing this right now. Works great. So supercritical water, about 350 degrees centigrade, 700 degrees Fahrenheit, about 22 bar or 35 atmospheres, you can make supercritical water. So heat it up, put it under high pressure, break the carbon-fluorine bond. We know how to do this, we do it for other processes, and it works well. some operational challenges, but it's expensive. To heat water up and to pressurize it takes a lot of energy. One step back from SQO is HALT, hydrothermal effluent treatment. A little lower temperature, a little lower pressure. You have to get the pH really high, and it's slower. But again, it works. There's a couple companies trying to commercialize this. This is what I've been working on, plasma treatment. I'll just take you through it real quickly. We have a small startup company, D-Max Plasma, trying to commercialize it. So what we do is we bubble argon gas through water, charge capacitors, discharge them over the surface, make little lightning bolts. Hopefully this video will work. That's one of our reactors, actually an old reactor, just generating little lightning bolts. These lightning bolts can break the carbon-fluorine bond, and we can get the PFAS up near this discharge using bubbling. Chemistry is interesting, largely unknown, but something we're working hard to understand better so we can optimize it. We use argon gas, as I mentioned, because it's easiest to generate plasma and argon gas, and then we recycle that argon gas so it's to keep costs down. Just some examples. So this is some of the compounds we're working on. This is treatment time in minutes. These were about gallon-sized reactors. And you can see within a few minutes we can get concentrations from hundreds and thousands of nanograms per liter below that target in a few minutes. Takes longer for the short chain compounds, as I mentioned there, harder to get to the interface. And interesting, so this work was done probably 5 years ago. Here our required treatment goal was 70 nanograms per liter. As I mentioned, now they're 4 nanograms per liter. EPA is advocating, at least before this prior administration. We can do this with ion exchange regenerant solution. Here, instead of parts per trillion, we're starting with milligrams per liter concentrations of PFAS. Instead of treating in minutes, it takes us hours. But again, we can get destruction. We're doing a lot of upcoming field trials on, so the Navy has a problem right on their Navy ships. They're using AFFF to fight fires, right, to save lives. That AFFF gets washed into the bilge. When the ships come in, they've got to exchange the bilge water. So the Navy's trying to figure out what to do with this bilge and oily wastewater from Navy ships. It's really a trial going on there. There's also some exciting moving parts I just mentioned quickly with ball milling. So ball milling, you're putting solids in a spinning reactor, hit them with stainless steel balls. And that seems to destroy PFAS very well. There's a lot of really interesting chemistry which you can generate with the ball milling process. And for the solids, which we've been struggling with, activated carbon, ion exchange resins, even potentially landfill solids. So it looks like ball milling might be a potential solution. We're working on groundwater and foam fraction. So, just take-home messages. PFAS are made up of a large number of chemicals, some of which we don't know what they are, and don't know how to measure them. Unlike the chemicals that we've spent all our careers and our predecessors and environmental engineers working on, how to get them out of water, PFAS are different because they're charged and they're highly soluble. And the carbon-fluorine bond is quite strong. So these are new set of problems we're not used to dealing with. We're grappling with that problem now. I've mentioned some of the technologies that we're working on to try to solve this problem. Like most environmental contaminants that we worry about, wastewater treatment plants don't do a good job. Water treatment plants, conventional ones, don't do a good job. Ones with membrane processes do separate PFAS. I already mentioned conventional problems with conventional approaches. And this will wrap up that our D-Max plasma has been supported by a lot of people. Lots of money by DOD put into trying to commercialize processes, find new processes, because they've got big problems on their sites. Typical costs. People talk about remediating DoD sites in the billions of dollars, worldwide remediation, people talk in the trillions of dollars, and that's probably too small. It's a problem that every environmental engineer is going to face. It's going to outlive me, and it's probably going to outlive the next generation of problems of environmental engineers. So, I don't want to be too much of a downer. It's certainly a problem. Concentrations are low, and they're toxic low. We're working on solutions. I think we will find solutions. Back to the talk before me, the people in the boardrooms of DoD or DuPont and 3M certainly weren't thinking about the environment when they made decisions to keep producing these products. It's unfortunate. Hopefully we've learned a lesson and that won't continue. So happy to answer any questions. Yeah.
So, okay, so let's say you remove it from the water. What do you do with it?
Yeah, that's, the destructive technologies are the only ultimate solution. So there are commercial processes, there are supercritical water oxidation. That's there are 3 large companies pushing that technology. We know it works, it's expensive, it doesn't work on low concentration solutions. So that's one option being pushed hard. Foam fractionation, that's being used at landfill leachates. It's relatively inexpensive, works well. We have this concentrated stream. Maybe we can put that somewhere contained until we can find a destructive technology that works. Maybe our plasma process will be one, but there are others. Yeah, it's everywhere. I mean, we can probably measure. I'm certain we can measure it on the carpet in this room from past process. It's in all our blood. Yeah, it's a world challenge for sure. Other.
Yeah. Have you seen any successes in like natural degradation, bacteria, fungi?
Yeah, that's a great question. So, environmental engineers, there are contaminants that we thought, environmental engineers thought had to be done with physical chemical processes. People have discovered the history of, so if you have a groundwater contaminated with a chlorinated solvent, for example, if you look around those sites, you can find bacteria that can utilize the chlorine to grow, either directly or co-metabolite with something else. And environmental engineers have cultured those bacteria, and now we can use them to clean up other chlorinated sites. So it's a great way of bioremediation, a well-known strategy. Unfortunately, we have not yet found bacteria that can break the carbon-fluorine bond, at least at measurable speeds. I'm not saying that will never happen, but so far we've not been able to find bacteria that can do that. There are plants that can uptake these compounds. So that's one strategy people are using in contaminated soils. You can plant certain trees, you can get the PFAS out of the ground into the tree, then you harvest the tree. You gotta do something with the tree, but at least you can get it relatively inexpensively out of the ground. So that's a strategy people are pursuing too. Other questions? Between you and lunch? Is that okay? Okay, so thanks for listening. Hope you learned a little bit about PFAS.